Let's begin our discussion of ionic bonding by looking at the noble gases and getting an idea of why atoms will bond to other atoms in the first place. The first thing we want to do is find the number of electrons in each one of these noble gases. Atoms are neutral, so the number of electrons is equal to the number of protons. And on our periodic table, we get the number of protons by looking at the atomic number. So let's go to family 8, the noble gases, and find out how many electrons are in each one of these noble gases. So helium has 2 electrons, neon has 10, argon 18 electrons, krypton 36, xenon 54 electrons, and radon has 86 electrons. Now let's consider the electron configurations of these noble gases, which you can also find underneath the symbol on your periodic table. So the electron configuration for helium is in the first period, and it has 2 electrons in its s orbital. It's 1s2. Neon is in the second period, so it has a 1s and a 2s and a 2p orbital, and all of those are full. Argon is in the third period. It has 1s, 2s, 2p, 3s, and 3p, and those orbitals are completely full. Remember, I'm getting this electron configuration by simply reading my quantum chart left to right, top to bottom. Now, krypton, we're going to use a little shorthand notation that is new to you. What we're going to do is put the noble gas before krypton in parentheses, and that indicates that the electron configuration up to this point is the same as argon. And then you start the electron configuration from there. So it's like going to argon on your quantum chart and then starting to read from there. So the electron configuration from there for krypton would be 4s2, 3d10, 4p6. So it's just an abbreviated version of an electron configuration. So we could do the same thing with xenon. The noble gas before xenon is krypton. So then we can start on our quantum chart at the next period, which would be 5s, so it'd be 5s2, and then 4d10, and 5p6. And then for radon, it gets a little crazy because you'll have some f orbitals, but xenon is the noble gas before radon, so the electron configuration would be 6s2, and then you have to go to the 4f's, 4f14, then back up to the 5d's, 5d10, and then finally 6p6. So these are the electron configurations for the noble gases. Before we look at this new concept of electron dot structures, let's make sure we remember what valence electrons are. Remember, valence electrons are electrons in the valence shell, which is the outermost energy level of any atom. So in the noble gases, these are the valence electrons. You will see there's a pattern there. Besides helium, which only has 2 valence electrons, all the other noble gases have 8 valence electrons. They have a full valence shell of electrons. That is why they don't react. They don't need any more electrons to fill up their valence shell. The whole purpose of bonding for atoms is to fulfill a full valence shell. What can they do to get 8 electrons in their valence shell? Noble gases already have that configuration. That is why they do not react. Let's talk about electron dot structures. So electron dot structures are a way to actually represent the valence electrons in an atom. It's a shorthand notation of your quantum model, really. So what you do is write the symbol, and then you use dots to represent the valence electrons. So helium has 2 valence electrons in its s orbital. So you put 2 dots above the helium. You can actually put the dots anywhere around the helium, but just put them together is the big point. They represent the electrons in the 1s orbital. Neon has 8 electrons in its valence shell. We're going to use 2 dots to represent the 2 electrons in the 2s orbital. And then, very similar to what we did with the quantum model, we're going to put 1 dot on each side of neon before we start doubling it up. So this represents like the p orbitals, each holding their own electron before having to share their orbital with another electron. So that is the electron dot structure for neon. For argon, we'd write the 2 dots representing the 2 electrons in the 3s, and then 1 dot on each side for the first 3 electrons in the 3p, and then pair up those dots with another dot to represent the other electrons in the 3p. Now, all the rest of the noble gases have 8 valence electrons, so their electron dot structures are going to look exactly the same. They will all have 8 dots surrounding the symbol. So the dots represent the number of valence electrons that atom has. So that was the electron dot structures for elements down a family. Let's look at electron dots going across a period. The first thing I want to remind you of is that whatever column or family that an element is in, that's how many valence electrons it has. So if we look at period number 2, family number 1, the first column, there's lithium. It's in the first family. It only has 1 valence electron, so it will get 1 dot in its electron dot structure. Family number 2 would have 2 valence electrons. It gets 2 dots representing the 2 electrons in the s orbital. Family number 3 is boron. Boron has 3 valence electrons, 2 in the s, so those are the 2 dots represented here, and then 1 electron in the p. Boron can also be represented by an electron dot structure by putting a dot on each side of the boron. Carbon is family number 4, so if we do its electron dot, we'd have 2 electrons in the 2s orbital and then 2 electrons in the 2p orbital. We can also represent carbon as an electron dot by putting 1 dot on each side of carbon, or we could represent it as 3 dots on one side of the carbon and another dot on the other side. Family number 5 is nitrogen. It has 5 valence electrons, 2 in the 2s orbital and then 3 in the 2p orbital, and we could put those on each side of the nitrogen. Oxygen is in family number 6. It has 6 valence electrons, so we can fill these electrons in just like this. 2 electrons in the 2s and then 4 electrons in the 2p. Fluorine is family 7. It has 7 valence electrons, so we'll start adding electrons and then doubling them up when we need to, and when we get to 7, we're done. And then we've already done neon. It has 8 valence electrons, so it has a complete valence shell. So that is how you represent the elements in period 2 as electron dot structures. Now, I would take the time right now to do something very important on your periodic table. Label the columns of the periodic table with the charge that their ions would have. So family number 1, all the elements of family number 1 are going to lose an electron to become an ion. That's why all of those have a +1 charge on their ions. Family number 2 is going to lose 2 electrons to become an ion. All of those elements have a +2 charge on their ions. Family number 3 will lose 3 electrons to get a +3 charge on their ion. Family number 4 could gain or lose 4 electrons, so it could be a plus or minus 4. Family number 5 is going to gain 3 electrons to become an ion. That's why they have a 3- charge on their ions. Family number 6 is going to gain 2 electrons, so they'll have a -2 charge on their ions. Family number 7 will gain 1 electron for a -1 charge on their ions, and the noble gases do not gain any electrons. They do not form ions. They have a full valence shell already. Like I said, the whole reason we're doing this is because only the valence electrons take part in bonding. So we don't have to represent all the other electrons in an atom. We only have to represent the ones that do anything. And that's why we use electron dot structures quite a bit when we talk about bonding.